So we spent a good deal of time exploring parametric equations / vectored valued functions, and at this point we've really explored these two paths quite extensively. We found that they represent the same path, but they're traveling at different speeds. And one thing you can do to kind of convince yourself without doing too much work that that these are the same path, you don't actually have to go through the process of eliminating the parameter. You can just take a look at how we might transform 2t to 4t. If we substitute into all of these t values right here, if we substitute t going to 2t instead, and then figuring out what that works out to be, right? 2 times 2t is going to give us 4t. Instead of t cubed, we put 2t cubed, we get the 8t cubed. And then again, replacing this t with a 2t, we'll end up getting an 8t squared. So if we can find some sort of substitution like that, then we can kind of see that they're following the same path. And of course, doubling the coefficient on t is going to double the speed at which we're traveling the path. So keeping that in mind, we might notice that this path right here, this logarithmic related path, might be the same path as the last two, because it's still 2 times variable, comma, variable cubed minus 2 times variable squared. It's the same pattern, right? So you can convince yourself, you can do some parameter elimination if you feel the urge. But what I'd like to do is ask the question, what do you think is going to happen about the speed here? How is using the log to define our speed going to change how this particle progresses along the path? So try to predict this on your own, and then explore. You can either click the link in the description below, or you can type that in, or you can just sit back and grab a bag of popcorn and watch what happens when I push play. Here we go. So again, this is the same idea as the other ones, and we'll see what happens. My computer was a little bit laggy there at the beginning, so it was hard to see what was going on. But look at how slowly this thing is progressing. You might notice that it didn't start off slowly. But at this point, it's going painfully slow. Now let's see this thing start over again. Oh, it starts out actually really fast. And if we think about what logarithms do, that's what they do, right? They've got this vertical asymptote. They don't exist on the left side of the vertical asymptote, and they shoot up really fast from negative infinity. Super quick. But then once they get to a certain point, they really start slowing down. And that's what we see going on here. So perhaps that's not terribly surprising. Something to keep in the back of your mind as you're looking at these problems. All right, so a few questions here that try to apply the concepts that we've already covered. You can use technology if you need to. My general rule of thumb is if you can do it without a calculator, then you should do it without a calculator. So we'll see how far we can get without a calculator, and then move on. So here's our position function, right? They're telling us it's a position function. So if we want the velocity function, velocity with respect to time, then we'll take the derivative of each component. So that's easy enough. We'll get 4t cubed for the x component, and 1 over t plus 1/2, 1 over t plus 1/2 for the y component. Well, that's really all there is. I mean, we could multiply the top and the bottom times 2 and get 2 over 2t plus 1, but you'll see in a moment that I'd rather not do that because of something called the chain rule. Because the other question we ask is for the acceleration vector. Now, I haven't mentioned the acceleration vector before, but it's fairly intuitive, I think. If we know how to get the acceleration in 1D motion, then we should know how to get the acceleration in 2D motion, because it's going to be just the derivative of the velocity, right? We want to find out how fast the x component is changing with respect to time. Now we're going to find out the second derivative here. So 4 times 3 is 12. Drop the exponent by 1 to get a 2. And the reason I didn't want to simplify this is because we can just think about this as t plus 1/2 raised to the negative 1. And that's actually a pretty easy thing to differentiate. We'll just take negative, and then the t plus 1/2 is going to be raised to the negative 2. So that's going to be that's going to be raised to the second in the denominator. All right. So yeah, just as you would expect, the velocity is a vector. We have an x and a y component. Differentiate each of the corresponding position components. The acceleration is another vector, and we do the same thing again to find the acceleration vector. So we can find the acceleration vector. We can also find the magnitude of the acceleration vector, just like we can do all those things with the velocity. So that's what the next question is asking, isn't it? It's saying find any values of t where the magnitude of the velocity is greater than the magnitude of the acceleration. Now, that's kind of an odd question, I think, because why would you be comparing the magnitude of the velocity and the magnitude of the acceleration? They're measured in different units, right? This might be meters per second, and this might be meters per second squared. So comparing the numerical values is almost meaningless. So this is not really an application so much as just a abstract exercise, I guess. But it's still fun to do, so we'll give it a try. The magnitude of the velocity, aka the speed, is the square root of 4t cubed squared plus 1 over t plus 1/2 squared. The magnitude of the acceleration, which as far as I know doesn't have a name, is the square root of 12t squared plus negative 1 over t plus 1/2 squared. And the question is, when is the velocity vector greater in magnitude than the acceleration vector? Now, I suppose we could try to do this algebraically, but I don't want to. So I'm going to go ahead and pull out my trusty pal, my graphing calculator here. And we'll start with a blank one. And we'll just graph these. Okay? Now, in a graphing calculator, you don't really want to type in t, because our graphing calculator doesn't think of this as the t-axis. It thinks of this as the x-axis. So all of those t's we're going to replace with x's. So for my magnitude of my velocity vector, I'll call that f of x, I guess, equals the square root of, let's see, we had the 4t cubed that was being squared. Oops, I just got finished talking about how we should use x instead of t. And we have the other thing squared, the other thing being 1 over x plus 1/2. All right, so there's a graph of the magnitude of my speed. Okay, g of x, or the magnitude of my acceleration, is going to have something squared plus something else squared. I like to type in the framework like that in case I get confused with parentheses later on. And we're going to get 12x squared here. And of course, we can leave out the negative because it's going to get squared. But I might as well leave it in there because it's there. All right. And we're interested in when f of x is greater than g of x. Oh, well, that looked pretty quick. So we can notice that the values over here with the negative values, we might remember that those actually don't make any sense, right? T has to be greater than or equal to 0. That's because we don't want this to be a negative. So we're making sure that we don't take the log of a negative or 0. So actually it looks like that starts around 3. Does it happen exactly at 3? I don't know. Let's zoom out and find out. Let's actually squash this down by changing that y value to something big. Maybe even bigger. And we can kind of see that, yeah, it looks like that's at 3. In fact, if we hide that, we can see that 3 is the value where they intersect. Okay? So anytime when t is greater than 3, it looks like we're going to have the red, being the magnitude of the velocity, is going to be higher up than the blue, which is the magnitude of the acceleration. And then anywhere else, it looks like the blue is going to be higher up. So according to Defmos, t is greater than 3. Those are the values for which the magnitude of the velocity vector is greater than the magnitude of the acceleration. All right, cool. And then we've got, I like these types of problems where it kind of gives you a family of functions and you just kind of have to talk about what the different values of the constant will do to things. So here we've got the same vector as before. We're just replacing the 1/2 with a k, where k is any constant. For what values of k? Oh, we put the absolute value bars there so that we don't have any negatives. At what value or values of k do the magnitude vector and the velocity vector look the same? Again, this is kind of a weird question because they're in different units, but it's still something we can ask. So how's that going to work? Well, we better find the velocity vector and the acceleration vector, and then we can have a place to start. So we know that p, let's do orange. Oh, goodness. P, I said orange. P of t is equal to t to the 4th, comma, natural log the absolute value of t plus k. So that means that the velocity vector and t plus k raised to the -1. This looks a lot like that last one, right? Because this is the same family of functions. And then we have 12t squared negative t plus k to the -2. All right, so that is the first step, right? We need to figure out what's going on with those particular values. Now we want to evaluate v of 3 and compare that to a of 3. So v of 3, we can evaluate that. That's going to be 4 times 3 cubed. And then we can evaluate, we're just replacing the t with 3. So this is going to be 3 plus k. K is something that we're looking for. We don't know what k is yet. And the acceleration vector, same deal, replace the t with 3. So we've got 12 times 3 squared. And this is going to be -3 plus k to the -2. Now, notice that in the x components, there's no k. It's just these two things are equal. Then 4 times 3 cubed and 12 times 3 squared better be the same. And they are, because if you think about taking one of these factors of 3 out of the 3 squared, changing it to a 3 cubed, changing it to a 3 squared, multiplying that extra 3 over to the 4, we get the 12. So yeah, it doesn't really matter what that number is. What matters is it's the same. Because that's the case, we can have a solution by setting these guys equal to each other. So we'll go ahead and do 1 over 3 plus k is equal to -1 over 3 plus k quantity squared. And there's our nifty little algebra equation that we can try to solve. We can multiply both sides by 3 plus k squared and get 3 plus k on one side and -1 on the other side, right? Now that seems a little bit odd because we're supposed to get 2 answers. Oh, yeah, actually, I see where I'm going with this. All right, so if we do that, then we actually only get 1 answer, k equals -4. All right? That's if we multiply both sides by 3 plus k. And before, I actually did some cross multiplying. I expanded this out, and I got k equals -3 and k equals -4. But I'm realizing now that k equals -3 is an extraneous solution. K equals -3 means that we have an undefined value for both of these guys. So only one solution here.